Hello friends and welcome to CEC live lectures. Friends, as you know that in science we have started a series on phase equilibria, and today we are conducting yet another lecture in the same series. In today's lecture we will continue with our discussion on solutions. It will be part 6 on the core topic of solutions. In this we will discuss the isobaric fractional distillation. To discuss this topic we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is assistant professor in Department of Chemistry in Dal Singh College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome sir.
Thank you so much, Amrit. First of all, I wish very good afternoon to all the dear viewers. Dear viewers, as you have been apprised of that this has been the 6th lecture in our series of phase equilibria under subtopic, that is solutions. Well friends, before we go to start with the topic matter or subject matter of fractional distillation, isobaric fractional distillation, we would like to have a quick recap of a prerequisite to the lecture and what has been already covered in the 5 lectures on the solution topics. So for that I would like to say that phase rule is central and needs to be applied in order to understand the phase equilibria, and we are trying to understand the equilibria between a solution and the vapor so formed out of this solution. So therefore this system should also be in compliance with the phase rule, and the phase rule equation says that degree of freedom F is equal to C minus P plus 2. When we go to make a binary solution, which is our part of discussion, so therefore here the number of components become 2. One, a constituent which constitutes the solvent, and the other which is basically a solute. So we have 2 constituents there. These are independent, so therefore they are also called components. So since when this kind of a liquid solution comes in equilibrium with its vapors, so we have 2 phases as well. So we have 2 phases and 2 components, so therefore C equal to 2, that is component equal to 2, and P equal to 2, that means number of phases also equals to 2. So therefore F degree of freedom equal to C minus P plus 2 also becomes 2 minus 2 plus 2, which ultimately leads to degree of freedom value to 2, numeric 2. What it means is that we can have at most 2 degrees of freedom. In order to define the system completely, there may be a number of thermodynamic variables like temperature, pressure and composition. Out of these 3, we have 2 degree of freedom. It means that we can only consider out of these 3 the 2 variables as independent, the third one become the dependent on the independent values of the other 2 variables being chosen. So for example, if we choose that the pressure and the composition be the 2 independent variables, and then in that situation if we choose pressure and composition be the 2 independent variables, those third one automatically the temperature becomes a function of these 2 variables, namely the pressure and composition, and therefore becomes a dependent variable. It means its value gets automatically ascertained by virtue of ascribing a specified value to the pressure and the composition. If we have to understand the isobaric fractional distillation, the term itself explains that isobaric means we have to carry out distillation process of liquid mixtures, liquid solution under constant pressure condition. So it means it is for sure that we will keep the pressure of the system constant. Usually atmospheric condition is being given to the system, and under atmospheric condition during the distillation process the pressure is kept at 1 atmosphere. Alright. So pressure is fixed. Now we are left with composition. If we fix the composition of the solution as well, then it means automatically the temperature will definitely be a fixed value for such a system which has this liquid solution having this specified composition between the two components which constitute this binary liquid solution, as well as the pressure being fixed, so that equilibrium temperature will be a fixed value. How we can view it? We can view it in a way that in order to have this pressure to a fixed value, we should understand what are the variables on which these vapor pressure of the solution depends. If you recall back to our previous lectures where we had derived the relationship or related the equilibrium vapor pressure of solution with that of the composition. So, as well as the vapor pressure of pure components. Now, this vapor pressure of pure components do depend on temperature. So long as you fix the particular temperature, so their values gets fixed. So ultimately the pressure becomes only a function of composition. Once you fix that composition, so in this manner, pressure will be fixed at a specified value if the composition and by virtue of temperature the vapor pressure of pure components gets adjusted. Both these values continuously change with temperature, the composition of liquid and vapor phase which are in equilibrium with each other, along with the vapor pressure of pure components at different temperatures. So therefore, the pressure in this manner, the equilibrium vapor pressure of solution gets fixed to a particular value. It means if you specify the composition of the solution, then it will definitely lead to a fixed composition vapor phase as well as a definite equilibrium temperature. It means equilibrium temperature means what? Whenever an equilibrium is established between the liquid phase and the vapor phase, and this occurs so only at the boiling point. So it means now boiling point of a solution is a function of the composition under constant pressure condition. As the composition of the liquid solution, the liquid phase changes, its boiling point also changes. This is what the inference is all about, which leads to the understanding of this graph between temperature and composition. Just have a look at this, the binodal graph which we had already explained in the previous lecture as well. But this lecture, if we need to understand isobaric fractional distillation, we need to understand under constant pressure condition what way we can change the temperature, or what is the sequence of effects by virtue of changing the temperature, namely the during heating process. That sequence of effects, once we understand, then this will lead to our prediction of or understanding of the isobaric fractional distillation. For that, just have a look at this temperature composition diagram. This is a binodal curve. You can see that TB star here represent the boiling point of pure component B on this temperature composition graph, and TA star represent the vapor the boiling point of pure component A. And at any point on this binodal curve, this is the lower curve is the one which is called liquidus curve, that has already been explained, and which gives the liquid phase composition, and vaporous curves is the above curve, and this represent vapor phase composition. So therefore, if you look at this point represented by point capital L, this point represent a liquid phase with composition given by this point capital X on the composition axis, and this liquid solution would be in equilibrium with its vapor given by which we can find its composition by drawing a horizontal line, that is tie line from this point L, which intersects this binodal curve having this vaporous curve at point V. So, point V, if we can draw the perpendicular on point V all the way to the composition axis, we will get to know the composition of the vapor phase. So, now if we need to this is what the temperature composition diagram is all about. Now, if we want to understand what is the sequence of effects if we try to heat a given liquid solution having a specified composition, that eventually will help us to understand what way we can carry out isobaric fractional distillation. So, once again have a look at the temperature composition diagram. On this temperature composition diagram, you can say that this is point small a, this is a point which represent overall state of the system. It means, and overall state of the system lies below this liquidus curve. It means at this point A, it resembles or it predicts a physical system in which there is only a liquid phase that is present. Now, it is important to understand that it is maintained at a temperature much lower than that of what is the temperature value for this composition on the binodal curve. So, what we will go to do is, if we want to bring vapors from, if we want to let this liquid solution to come in equilibrium with the vapor phase, then we need to heat it. That is, you can say, you can once again see from the phase diagram itself, from point A, which represent overall state of the system. Initially, if you try to heat the system, what is the meaning of heating the system is that you are trying to raise the temperature of the system. So, what it means that a system which was initially at point A, that is now being shifted to point L by virtue of continuously heating the system and raising its temperature. Once the temperature of the system reaches to point this point capital L, this is the temperature. This binodal curve predict that this is the temperature for this liquid composition solution, which is its boiling point. So, obviously at its boiling point, this solution will come in equilibrium with its vapors, and therefore this liquid solution will now come in equilibrium with its vapor, that is represented by this point represented by point V. So, now you can see only a first trace of vapors are formed. As soon as this vapors is formed, now what will happen? You can see from the diagram itself, this point V lying right to the right of point L, it means is that proportion or amount fraction of component A in the vapor phase is greater as compared to proportion of component A in the mixture corresponding to point L. It means vapor phase is richer in the component A, and component A having its pure boiling point lesser than that of component B. So, it means component A is more volatile. So, therefore, vapors which gets formed are richer in more volatile component, and this is basically the basis of this distillation process as well. So, now it means as soon as these vapors are formed, the liquids which so remains thereafter will be having will be richer in proportion of less volatile component, or in other words component B. So, if we want to now bring this remaining liquid to come in equilibrium with vapor, once again what we need to do? We, after collecting this initial formation of vapor V, it means that we need to heat the system to another temperature, so that it comes in equilibrium with its more vapors, but that will occur at higher temperature, because proportion of less volatile component has increased in the remaining liquid. So, it will boil at a higher temperature. So, in this manner we can say, if we heat this liquid solution further to point A dash, as you can see from the figure, at point A dash, which is having greater temperature corresponding to temperature T, at A dash you will see that at A dash you will have liquid phase having composition L dash and vapor phase having composition V dash. So, what it means is that the two components has redistributed themselves in the two phases such that quantity of vapor phase has grown and the quantity of liquid phase has depleted, and the relative amounts of the two, that is the liquid phase and the vapor phase, can easily be predicted from the lever rule. Now, when you further heat the system to the temperature corresponding to point V double dash, at this point whole of the liquid solution has vaporized and only a last trace of vapor so remains. And this can be looked at very easily, that initially when you had started vaporizing, there was huge amount of liquid, only a first trace of vapor. So, overall composition and the liquid phase composition was coinciding, but now when all the liquid has vaporized, only a last trace of last drop of liquid has remained. So, now at this point liquid phase composition is much richer in low volatile component, whereas overall composition just matches to that of overall composition just matches to that of vapor phase. So, beyond that there is only, if you further raise the temperature, then the overall system, even the last drop of the remaining liquid will do vaporize and you will have only vapor phase, and that will be beyond binodal curve. This is what is the sequence of effects which we have discussed here can be used to understand the isothermal fractional distillation. For that, just have a look at this. If you have a, suppose initially if you have a liquid solution corresponding to having composition corresponding to point A. So, if the overall state point also lies at point A, then what you will do in order to bring it in equilibrium with vapor phase, you will heat it at point A dash, you will have formation of vapors corresponding to point B double dash. Now, these vapors you can collect and you can decrease their temperature, you can condense them that way, and you can get the condensate formed corresponding to this point small b. Now, this condensate can also once again be heated and brought to this point B dash. Now, this condensate will come in equilibrium with its vapors. Now, its vapor you can see represented by point C double dash, and point C double dash is having the composition which is having greater proportion of component A, which is more volatile. So, once again you can collect these vapors, you can condense them, you can get the condensate represented by point C, and then you can once again heat this condensate and all the way you can bring it to point C dash. At point C dash, this liquid condensate will come in equilibrium with its vapor, which you can understand from the tie line. Their composition will be corresponding to point D double dash, and now this vapors you can once again collect and you can once again condense them, and this once again you can heat, and then ultimately it will lead to vapors which will contain only pure component A. So, my point is that if you have a liquid mixture, and by virtue of distillation you want to separate the two components or two components of the liquid solution, liquid mixture, then what you need to do is you have to heat it and you have to raise its temperature, and up to a certain temperature then you will let it come in equilibrium with its vapor. Then you need to collect those vapors, then you need to condense them, once again bring the condensate and once again heat it to its boiling point, once again let it come in equilibrium with its vapor, collect those vapors, once again make a new condensate, once again the condensate so formed, once again let it be heated to its boiling point, once again you can say that it will be vaporized by virtue of reaching it to its boiling point, and then those vapors can also be collected once again, and those vapors which so collected will also be condensed once again and can be subjected to further and further boiling, and ultimately a stage will be reached where you will have pure component A or less volatile component A emerging from the vapor phase only. So, On the contrary to this is that the fact that in the liquid phase you will have less volatile component proportion continuously increasing, and ultimately the residual liquids which has remained after collecting condensate, at every step you will mix them up once again, and ultimately you will keep on repeating the exercise, and ultimately you will find the liquid solution which remains ultimately in the final pot, that will contain pure component B, that will be less volatile in nature. So in this manner you can separate component A, which is more volatile, in the form of vapors. You can collect them as condensate, and you can form it under the as liquid phase, and whereas remaining liquid of this distillation process will eventually lead you to the pure component B. So in this way in batch wise process you can carry out isobaric fractional distillation. That's what we have tried to understand. We have tried to understand the very basic, very underlying principle behind this fractional isobaric fractional distillation, how we can carry them, and of course compared to isothermal fractional distillation, it is very easy to do. So with that we will continue with the application of this understanding, how it leads to the discussion of fractionating column and non-ideal systems. For now, thank you so much.
Dear friends, so far we have done isobaric fractional distillation, and we will continue with our discussion on solutions after the short break. We'll take a break now. Thank you for watching. Thank you. Dear friends, welcome back. So far we have discussed in phase equilibria, so in solutions part 6 we have discussed the isobaric fractional distillations. Now we will continue with fractionating columns and non-ideal solution, as well as Denham-Margulis equation. To discuss this topic we have with us the same speaker, Dr. Amit Kumar. Let's welcome him and start the topic. Welcome, sir.
Thank you. Dear viewers, as you know that we have been having discussion on isothermal fractional distillation. So what we are going to do in this module is that we will make use of understanding of this isobaric fractional distillation. We will apply in order to understand the functioning of fractionating column, and why we need to do the distillation using this fractionating column. That is important to understand. If you remember back while we were having our discussion of isobaric fractional distillations, we were carrying out distillation in batches. At every stage we used to collect vapors, and we used to condense them, and after condensing them we used to once again brought them to their boiling temperatures, and used to once again had their vapors. But that was a very tedious process, and eventually it is a tedious process for anybody, for any experimentalist, to collect vapors at every stage of the distillation process. it is very helpful if we can have a continuous kind of an isobaric fractional distillation in a continuous manner without collecting the vapors in batches at every stage. That can be done using a fractionating column, and for that we need to just have a look at the figure itself. This figure is very known figure. Ever since your 12th standard, 10th standard, you have been studying the distillation of petroleum products, where you had been having exposure of this fractionating column. Basically, this fractionating column is designed in a way so that you can imagine a very long tube in which there is a gradient of temperature along the height of this long tube. A tube, you can say, or as you can say a big kiln or so. So at the bottom of this tube kind column, at the bottom there will be a lot of liquid solution that has been filled there, and at the bottom in fact there is a heater, and at the top there is a condenser. That is the basic essence of this experimental setup. It means whenever you have introduced the heater at the bottom, it means temperature will be much higher at the bottom, and so therefore as you go up the column or up the tube like column, you will observe a gradient, a difference of temperature. Temperature will continuously decrease as you go up the column. So it is very clear that if in this tube like column there has been various levels, or you can call them as plates, where thin film of liquids can be collected, and in fact there are narrow openings at every plate, and which are being provided with their caps. They are being called bubble caps there because the vapor so emerges. When the vapor emerges from these openings, that gets condensed and the liquids are formed. Because of this cap nature of this capping, bubble like slanted nature of this capping, the liquids which gets formed as a result of condensation gets collected onto this as thin film onto this slab or this plate, and whatever the vapors whose composition still is according to the temperature, they can exist as vapors because their condensation temperature is much lower. So they can once again emerge from these bubble caps all the way to the above plate and can get condensed at even lower temperature. So in this manner, liquid of different composition gets collected at every slab or plate, and the vapors which still having the composition, according to the composition the liquefaction temperature is much lower. So these vapors can emerge to even higher plate, and therefore they may condense at that higher plate. So it means there will be a liquid mixture of a particular composition at temperature T naught, that is 0 plate. At first plate there will be another liquid which will be having its boiling point corresponding to temperature T1, and T2 will be the boiling point for the liquid composition which gets collected onto this second plate. T3 and T4 therefore are still lower temperatures. Now how we have just seen that how this column operates, that is heated at the bottom and condenser is introduced at the top. So there is a different temperatures at different slabs, and at different slabs according to the temperature a liquid of particular composition gets collected, because we have seen in the temperature composition diagram that for a particular composition of a liquid to come in equilibrium with its vapors, it need to have a fixed temperature, that is its boiling point will be a fixed value. So liquid L1 will be having its boiling temperature T1, L2 will be having its temperature T2, L3 liquid will have its boiling temperature T3, and L4 liquid having specified composition, which we will go to understand very shortly, will have its boiling point T4. If we need to understand the very basic, we can see over here the maximum boiling point in this diagram, you can say, is of boiling point of less volatile component, that is component B. So, TB of TB star is a higher value, because the component B is a less volatile component, and more volatile component is component A, so is having lesser boiling temperature. So, any liquid mixture which will be having a greater proportion of component B, obviously then it means will have its higher boiling point. So, if we have a liquid mixture, suppose where the pointer is pointing out to be, suppose this is the liquid mixture having this composition, this point. If you heat this liquid mixture, it will continue to remain as liquid. So, therefore, it require greater temperature. That is how you can see liquid L0. You can say this is the liquid L0, which now when is heated to temperature T0, it comes in equilibrium with its vapor and forms vapor V0. So, it means this liquid at the bottom, which is L0, that lies at the bottom, and the vapor V0 emerges from this liquid plate level and reaches all the way to the bubble caps in the first plate, and there some of the liquid gets condensed and vapor V1 is formed. So, here what happens is that liquid vapor V0 which reaches the plate number 1, number 1 is having a temperature, lesser temperature T1. So, V0 point, you can say that approaches to point A. At this point A, there is a liquid phase. Now, some of these vapors, some of the vapor amount gets condensed, having this liquid phase composition. L1 and V1 is the proportion or composition of vapor phase which still emerges from the plate number 1, or you can say the slab number 1. This here you can see it's still the vapors which emerge is these vapors which reaches slab number 2. So, you can see at slab number 2 the temperature is still lower T2. So, you can say the vapor V1 when is brought down to temperature T2, this is temperature T2 at these vapors corresponding to point V1 when go to temperature T2. Now, these vapors comes to overall composition of these vapors becomes represented by this point B, and now this some of them gets condensed and form some liquid, and that liquid will have, according to this tie line, will have composition L2, whereas vapor phase will have composition V2. Now, these vapors still emerge from plate number 2 and reaches plate number 3 over here. So, plate number 3 when they reach, so temperature gets decreased to T3. So, overall state point you can see vertically goes down and reaches to point C, where you can see from where the pointer is pointing out to be. And now this at point C, these vapors at this temperature T3, some of them gets condensed and form liquid phase corresponding to composition L3, whereas vapors which still some of the vapors still remain vapors. So, that is having the component, that is having the composition corresponding to the point V3. These vapors further when go to even higher slab, the slab number 4, they reach to temperature T4, and ultimately some of them get condensed, and therefore once again at this plate liquid L4 therefore comes in equilibrium with vapor V4. So, you can see automatically if the liquid gets increased over a particular slab, you can remove this liquid, or it can ultimately through the overflow mechanism, if this gets filled more, it can get decreased, it can get slanted all the way to the lower slab, that is higher temperature slab. So, there is a redistribution of liquid phase, vapor phase at all these slabs, and ultimately you will observe that the vapors which emerge from the top, that will be comprising of vapors which will be having only pure component A, that is low volatile component, and ultimately their temperature will be reached at the bottom where you can get the pure component B in this manner. So therefore, in this manner this fractionating column helps us to continue with the distillation process in the continuous manner. We need not collect these batches, again and again, and we need not condense them over and over again and again, and it gets ultimately in this fractionating column helps us to redistribute the liquid, the vapor, and in a continuous manner. Ultimately from the top the pure component vapor phase can be obtained, and the remaining liquid at the plate L0 will be having the pure component B, the lesser volatile component. That is what is the fractionating column. That is how it helps us to carry out fractionation or isobaric fractional distillation in a continuous manner. Right. After having this, it is very important to still understand that the isobaric fractional distillation which we have discussed yet is only for ideal systems, or for those systems that is binary solutions which are ideal in nature or which does not deviate much from ideal behavior. So what is the deviation, or if deviations from ideal behavior occurs, what way we approach them? In order to understand that, we need to understand the node ideal solutions. So just have a look at this. Node ideal solutions, there are two kind of known ideal solutions. One is which exhibit positive deviation from Roult's law, and the other which exhibit negative deviation from Roult's law. Now what is this deviations? In a situation when the tendency of molecules of each kind to escape from the solution to vapor is greater, the solution is non-ideal and is said to exhibit positive deviation. Why it is so? When the tendency of the two components is more to escape, it means the greater quantity of vapors will form, and therefore vapor pressure at a fixed composition corresponding to a situation where Roult's law is followed, it will not be the situation, and the equilibrium vapor pressure for that composition in this non-ideal system will be greater. So therefore, greater vapor pressure than what is predicted by the Roult's law for a particular composition of a binary liquid system, then we call such a situation as we are dealing with non-ideal solution having positive deviation from ideality. So this deviation is larger when the two liquids differ greatly, and a maximum is observed in pressure versus composition curve of solution is very large positive deviations occurs. Now what are the factors upon which this positive deviation exists? Occurring of positive deviation depends. These factors are difference in polarity of molecules. If you have one liquid component which is polar in nature and the other as non-polar in nature, or their dipole moment differs greatly, so that is the situation, the one situation on which accounts for positive deviation from ideality. Difference in hydrocarbon chain or analogous grouping of molecules, it means is that if we deal with the two organic liquids having organic compounds, if they have same functionality but differ in a homologous series, the number of CH2 groups which they have in the chain length, if that varies, then that also leads to deviation from ideal behavior. Now third thing is that difference in intermolecular forces of attraction. If there is a huge difference in greater the difference in intermolecular forces of attraction between operate between the molecules of between these two molecules of different liquids, then of course there will be much more positive deviation resulting out of this difference in intermolecular forces. Now association of one of the liquid or dissociation of the other, these are also the factors. If suppose one liquid do associate in the liquid system, for example benzoic acid and acetic acid, they do associate in the liquid system. So therefore, if that goes on, that also leads to a factor which brings about positive deviation from Roult's law. Let us discuss the examples. The first example is carbon tetrachloride and haptane system, that is at 323. Let us have a look at what this solution has in store for us. The solution shows small deviation. Why it is so? Both constituents are non-polar and involve low forces of attraction. So on account of only one factor, so this solution exhibit positive deviation, but the deviation are small. Now compared to this, if we look at ethyl ether and acetone at 293 and 303 Kelvin, deviation in this solution is larger, and this results because these two different molecules differ appreciably in intermolecular forces compared to the first situation where carbon tetrachloride and haptane molecule were dealt with. The intermolecular forces were not the difference between them was very low, but over here they differ appreciably in when you compare ethyl ether and acetone. So therefore this is the reason the deviation becomes more. Compared to this, if we have haptane and ethyl alcohol is dipolar in nature. On the contrary, haptane is not polar in nature. So not only this, there will be you can say grouping of homologous series. Ethyl alcohol has only 2 carbon atoms, whereas haptane has 7 carbon atoms, long hydrocarbon chain. So this is another factor. Polarity, chain length, intermolecular forces of attraction also differ greatly because of, you can say, ethyl alcohol which is dipolar in nature and haptane which do not have dipole moment associated with it. So therefore all these factors are contributing towards positive deviation from ideality. So compared to the earlier examples, all these factors are figuring here in this example. So therefore you can understand that this solution will exhibit very large positive deviation from ideality. So you can see in this order for these 3 liquid systems, we have been having a continuous increase in the deviation from the ideal behavior. Right, these characteristics we can sum up for non-ideal systems having positive deviation. You see, when the positive deviation means low forces of interaction between the two compared to their pure molecules. So therefore enthalpy of mixing will be greater here in this sense. So delta H mixing will also be, and delta G. Right, in comparison to this negative deviation from Roult's law, if we discuss here, what occurs is that negative deviation means the vapor pressure of an equilibrium solution of a binary liquid system. What is predicted by Roult's law is not actually the situation practically. Its vapor pressure is much lower compared to what is predicted by the Roult's law for a particular composition of a binary liquid solution. Why this is so because if the force of interaction which operate between the two A molecule is less compared to 2B molecule, and if in fact if we compare it with between A and B kind of molecule, it is much greater. So therefore the enhanced force of interaction which occurs in the two different molecules. So therefore this leads to kind of a situation where volume gets decreased, and therefore the molecules come more closer. It becomes difficult for them to vaporize, so vapor pressure gets decreased. So this is about this negative deviation from Roult's law behavior. So we will intrude upon this non-ideal behavior a bit more, and we will do Duhem-Margouel equations. So I think we may have a question or two if we have. Alright, so since we do not have the question, so we can continue with this discussion. Right, so vapor pressure of constituents, as I said, lies below of that of ideal lines for this negative deviation from ideality, this kind of a behavior. So, these examples of this system is pyridine, formic acid, acetic acid or propanoic acid. That means organic acids, when they are coupled with they are mixed with pyridine, they form a solution which gives this negative deviation, but since deviation is lower. So, chloroform, ketones, ester, chloroform with ketone, ester, amines, etc. These kind, the deviation become even more pronounced. An aqueous solution of strong volatile acids, HCl, nitric acid, etc. So, aqueous solution here, water and nitric acid, by virtue of hydrogen bonding, they form greater interaction which operate between the two different kind of molecules. So, therefore, much more pronounced deviation. So, here delta H is even lesser compared to ideal system, which is 0. So, is negative, delta S mixing is negative, delta G mixing is not equal to delta G ideal, which is less than 0, but here, and delta V mixing is also less than 0 and PA is less than PA ideal. So, after this we will have to discuss the Duhem-Margouel equation. This equation helps us to understand very many ideas, very many interpretations about both ideal and non-ideal systems. So, that we will do in our next lecture. For now, thank you so much.
Dear friends, we hope that with today's lecture you were able to understand various aspects of solutions. On that note, we would like to thank Dr. Kumar for coming here and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.